Okay, so last time we were we were looking at what are the general quantum operations. So we we might look at that. So classical. Okay. And the first one was attach. So I'll introduce a term called ancilla. So this stands for ancillary bits. That means extra bits. Ancilla bits. Initialize to 0 and random con. Okay. Then so plus reversible deterministic algorithm to joint. Joint register means input plus ancilla. Joint register. Something wrong with this pen today. So bad. And
Maybe turn it off on and off again. Disconnect and
yeah, let me try. I think maybe the name has to be changed. Okay, number 3 is no, discard and yeah, let me try. Trackpad is fine. Okay, let me try. Hmm. Okay, let me try a suggestion. See how this goes. So attach. Not really better. Ancilla. Okay, so attach ancilla. So let me introduce this term qubits. So, so what is qubits? So what was classical bit? We all know. So bit was a two-dimensional sample space for us. So it's a sample space which has two elements, which I'll call 0 and 1. And a qubit, the quantum analog. Okay, so it's a quantum system whose Hilbert space is the two-dimensional space over complex number C2. And I think something has gone wrong with it. I'll have to change that. So qubit and remember, I mean, we have a two-dimensional space, so we fix a computational basis. Okay, so which I'll call ket0, ket1. Okay. So in the column vector notation, so the standard basis 1, 0. C and yeah, so this is span. I think. Okay, and so attach ancilla qubits initialized to. Let me write a bit slowly. I think better initialized to. Okay, 0. So 0 means they're initialized to the.
You can say, and I can write on my machine if that's better.
No, it's not so simple. So several zeros out here. So let me say. Okay. So what is this? So this is the diagonal density matrix. So remember ket0, and this is what is called bra0. So bra is just the conjugate transpose. So ket0 was the computational basis, the first computational basis vector. That's the zeroth computation basis vector. Ket1 is the first computation basis vector. So in terms of standard basis, it's 1, 0. Then its conjugate transpose will be this. Okay. So multiplying a column vector by a row vector. So this gives a 2 by 2 matrix, which has a 1 in the diagonal and zeros everywhere. So this is basically a diagonal density matrix. So diagonal density matrix is a probability distribution, and as you can see, all the probability is concentrated on the element 0, the computational basis vector ket0. So this is the analog of the quantum way of expressing the classical statement that the ancilla bits are initialized to 0. So attach ancilla qubits initialized to all zeros. So I put this notation 0 with the vector arrow sign to indicate that there are several of them, and they're all initialized to a state ket0, tensor ket0, tensor ket0. Okay. And recall that I had said last time, I don't need to initialize some qubits to some random states. As you will see, like our quantum operations that we allow will allow us to simulate random. So all we need is some ancillary qubits or workspace initialized to ket0. So this includes both the work bits here and the random coin bits. Okay? All of them are initialized to ket0. Any questions about this? Yeah. Yeah. Okay. Number 2. Then a deterministic algorithm, remember, was a permutation of input bits. permutation of all the bits. Okay. So the algorithm is applied to the original input bits and the ancillary bits. So now I'm going to apply unitary. At least here it is. Transformation. Original. And I think it is the deepest call. Because now if I apply a little bit of pressure and write, it's coming out better.
Oh, that means the nib is, you have to change the nib.
Yeah.
But how
Yeah.
old is this pen? My pen, I've been using the same nib for more than 2 years now.
No. This is of course not that old.
Ah,
No. But the nib also looks a little shorter than before. I don't know, maybe it rubbed against something.
no, nibs expire. Nibs expire. Nibs are supposed to expire, but not this quickly.
Not this. Yeah.
I mean, with my pen, they send extra nibs. Okay.
Yeah. I also extended somewhere. But yeah, I didn't expect this will happen so far. But maybe this rubbed on something.
Oh,
Okay. So and the last one is of course discard and select it. Okay. Okay. So let's understand what this statement means. Okay. So let us see what the quantum thing is with me. Right. So there was.
Pranam, I just had a question. So, this the Kedbra operation, is that the wedge product?
No.
Then what is it? I mean,
This is
you can
just
cook up.
this is just matrix multiplication.
This is
So
matrix
that
multiplication, but yeah, matrix, but it's
just matrix multiplication.
it's a weird sort of matrix multiplication, right? It takes two smaller matrices and puts it on a high dimension.
It's multiplying a column matrix by row matrix. It is
Sorry.
matrix multiplication. So if you want to view it as linear transformations,
Yes.
So what is BRAC? Conjugate transpose is what? Conjugate transpose of a vector. Okay, so if a column vector gives a row vector. So what does it mean? A row vector is what we call linear function.
Yes.
So it maps vectors to complex numbers.
Yes.
Okay. So what is a row vector doing? Given if I were to put a input vector v out here, so changing the color.
Color is to the right.
Maybe this. Yeah. So if I put in some vector a comma b out here, so then this row vector times the column vector will give me a scalar, will give me a complex number. Okay. And this row vector is a linear map from the tuples a comma b to complex numbers, right? So this is a linear function. A row vector I'll interpret as a linear function. Okay. And so bra is basically linear function. And ket, as I said, was a vector, but I can think of a vector as a mapping from the one-dimensional space to the two-dimensional space. So what do I mean? So
you're going from n-dimensional space to one-dimensional space to m-dimensional space.
No. So this is cat Brano. So both are n. If this is if the original thing is an n tuple column
No,
vector, this
so
is an n tuple
the
row
way
vector.
you described it is linear functional composed vector composed with linear functional. So linear
Yeah. So
functional is from n dimension to one dimension, and then from you map from one dimension to again a larger dimension. That's what I meant.
yes. So what do you mean a vector composed linear functional? So the linear functional part you have got. So this is a row vector. It multiplies AB. So this gives a scalar, and the scalar goes and multiplies this vector.
Yes.
Okay. This is a fixed vector. Okay. But I mean, if you really want to, I mean, make sense with multiplication matrices, you can take a fixed vector as representing a linear functional from C1 to C2 out here in this case. So C1 to Cn in general. So take the one-dimensional space over complex numbers. Okay, take a basis vector. So one-dimensional space over complex numbers, as I said, is the set of complex numbers only. And take a basis vector. Let's say I take the scalar 1. Okay, everything else is a scalar multiple of 1. Right? Every complex number is of the form alpha times 1. So I'm talking of the function which sends the complex number 1 to this fixed vector. So it will send the complex number alpha to alpha times this fixed vector. Okay.
Right.
So if I view it that way, then the row vector maps, in this case, a 2 tuple to a scalar C1. So the row vector is mapping C2 to C1. The column vector is mapping C1 to C2. So overall, I get a map from C2 to C2, which is this 2 by 2 matrix. So it is matrix multiplication. Okay. So matrix multiplication, which is nothing but composition of linear maps. So a column vector times a row vector can be viewed abstractly as a composition of linear maps.
Okay, got it.
Yeah. So, yeah, Hari, is this clear?
Yeah.
So some abstract reasoning. Okay. Let's get back to our business. So I started off with a system which I'll describe by some density matrix. Okay. So let us say this is the density matrix on the input system. Let's call it I. Okay. And then I've attached the ancillar space. So okay, let's do the steps. So I started off with rho I. And then I'm mapping it to rho I tensor. So what I'll call the all zero state on the ancillar A. Okay. So after this, I'll apply the unitary transformation. Okay. So remember, U is unitary transformation on the total system, input and ancillar. So I'll call it U with superscript IA. So what does this go to? Let me write it down. So the definition of applying unitary transformation is, so I know what the unitary transformation does on a vector, right? It multiplies a vector from the left. When vector is a column n tuple, it multiplies it from the left. Now remember my row, okay, it's a matrix, it's not a vector, but like taking an idea from here, a matrix is nothing but a column vector times a row vector. At least, I mean, some matrices look like that. And with some thought, you can see that a general matrix can be written as a linear combination of these matrices. So these matrices are matrices which look like column vector times row vector. So some more thought will tell you. So what is an algebraic column vector times
Eigenvectors.
No, let's not go so fast. So what is a column vector times a row vector? It's nothing but a rank one matrix. So now if you think of abstractly, what is a rank one matrix? So the output space is one dimensional. Okay. So a rank one matrix maps the input space to a one dimensional space. Okay. So then with some thought, you can say that any rank one matrix can be thought of as a column vector times a row vector. Okay. May not be the same thing. In this case, it's the same, but a general rank one matrix is a column vector times a row vector. Okay, so this is a precise description of rank one matrices. Okay. So every rank one matrix can be thought of as a column vector times a row vector and vice versa. Yeah. So, so this gives an idea what the action of U on matrices should be. Okay. On vectors, I know it. it will multiply the column vector from the left. But now there's a row vector also. So the row vector, it has to multiply from the right. But remember, row vector was conjugate transpose. At least in this picture, it was the conjugate transpose of vectors, right? So the bra is the conjugate transpose of kets. So I have to do a conjugate transpose of the unitaries also. So to cut this story short, so this is U. Then remember, it is so I tensor 0A. Okay. So this is multiplying the column vector on the left. So think of row as something looking like a column vector times a row vector. Okay. Ket times a bra. So the ket gets multiplied from the left, the bra will get multiplied from the right. But now I have to multiply by its conjugate transpose. In the quantum notation, this is usually denoted by the physics notation, which is dagger. So this is the conjugate transpose. Okay.
So Pranab, I just had a couple of questions about this.
Yeah.
Yeah. So the first question is that, I mean, we always do the conjugate operation, because I mean, one reason I can think of is that you want, I mean, after you operate a unitary on a quantum state, you want it to remain a quantum state. And what is a quantum state? It's it has to be a positive semi-definite matrix, right? So that's why you have to do the conjugate, because if you do the unitary just on one side, either side, it's not guaranteed that it will remain a positive semi-definite.
Correct. So yeah, so what you're saying is that, like, the thing in the brackets, of course, is a positive semi-definite matrix. It's a density matrix. Okay, so it satisfies, yeah, positive semi-definite trace one. Okay. So, and I mean, you can easily check that in fact, the tensor product of two positive semi-definite matrices is a positive semi-definite matrix. Okay. So recall I defined the tensor product to the Kronecker product of matrices, and then you can check with some, maybe a little bit of thought is required, that the tensor product of two positive semi-definite matrices is a positive semi-definite matrix. Okay. So let's see. So maybe the quickest way to see it is, so remember, like, first of all, positive semi-definite matrices are Hermitian. So first of all, check that tensor product of two Hermitian matrices is Hermitian. So this you can easily check from the definition, okay, of Hermiticity. So that you can check. So you can be sure that this is a Hermitian matrix. And then once a matrix is Hermitian, if its eigenvalues are non-negative, then I know it's positive semi-definite. So it's one equivalent characterization. So then you can check that if I bring tensor product of two positive semi-definite matrices, then you can check that the eigenvalues just multiply up. Like, take an eigenvalue from the first guy, take an eigenvalue from the second guy, and then multiply all such pairs. So this is the complete list of eigenvalues of the resulting matrix. So this you can check, and the eigenvectors are also the corresponding tensor products. So this is where you require some thought, but it's pretty straightforward. So the tensor product of two positive semi-definite matrices is positive semi-definite matrix. And I just told you what the eigenvalues are. The eigenvalues multiply up in pairs. So the sum of the eigenvalues is 1 here, sum of the eigenvalues is 1 here. So the sum of the eigenvalues in the product out here will also be 1, right? So yeah, so tensor product of density matrix is the density matrix. So any questions? Sorry? Saying something?
Oh, sorry. No, it was my background. Sorry. Oh. No, I kept my mic on because I was going to say something more after you finished.
Yeah. Okay. Yeah. So this quantity inside is a density matrix, and now I'm going to, if I just multiply it by, I mean, U on one side, and you can check that in general it's not even Hermitian. So to preserve Hermiticity, you have to multiply by U and U conjugate transpose here. Then you can check it's again Hermitian. Okay, and you can again check its positive semi-definite. So this is easy to check. You can check by the action on vectors, for example. Or if you prefer eigenvalues and eigenvectors, so this is simulated transformation. So this will preserve the eigenvalues. But if the eigenvectors were v1, v2, v3, so on, the new eigenvectors will be uv1, uv2, uv3, dot. So this also you can check. Yeah. So yeah, Shandan, you are still saying something?
Yeah, maybe this is a sort of an abstract nonsense question, but this for basic group theory, right? You have these operations called normal transforms, or like normal
Normal
subgroup.
matrices, you mean?
I'm just coming from the most abstract group theory. So basically, suppose you have a subgroup H of a group G, right? And you can cook up operations like A, B, A something, A B A inverse, right? A B A inverse, or B belongs to H.
Okay.
And these sort of maps have some very special properties, right? So I mean, this looks like that. This looks like that. This looks like normal transforms, normal.
Yeah, it's kind of yeah.
Not being
I
very
mean,
clear about this, but sorry.
yeah, I mean, at least syntactically it looks similar. See, but I mean, like U dagger is also U inverse. So,
Yes.
so these are similarity transforms, and we know what similarity transforms do to matrices. So they preserve the eigenvalues and they change the eigenvector. So it's basically like a change of basis. So if the eigenvectors were v1, v2, v3, so on, and if I do a similarity transform, so the new eigenvectors will be u v1, u v2, u v3, dot dot dot. Okay, but the eigenvalues will remain the same. So I mean, in that sense, a similar transform is a change of basis. So this is a change from one orthonormal basis to another. So here the change of basis transformation is unitary, which basically means that I'm changing from one orthonormal basis to another. Yeah, okay. So there are similarities, but at the moment, I mean, what you're talking of is normal subgroups. But yeah, I mean, let's not drive that too much. I mean, out here.
Okay.
So yeah, but yeah, the syntactic form is the same. So, and definitely, I mean, you can make, you can make statements that if the thing inside is Hermitian, and if I conjugate by unitaries, then it remains Hermitian. So in that sense, like the
yeah, it's invariant under these maps. That's
yeah. But then, for example, the set of Hermitian matrices does not form a subgroup.
Normal, yeah, it does not.
It does not form a subgroup at all because product of two Hermitian matrices in general not Hermitian.
Is not Hermitian, yeah.
Yeah, so it doesn't go much beyond that observation.
Right. Okay.
So, questions? Hari, is it clear?
So this so we would like to have this Hermitian property even after pre-multiplying with U and post-multiplying with U dagger, because this is also, we would like this to be a density matrix as well.
Yeah, exactly. Because classically at each step we had probability distribution, right? So
okay,
yeah. So and I mean, then you can immediately see that if you have somehow decided that the analog of the deterministic algorithm will be unitary transformation, I mean, this is the natural thing to write. And I mean, maybe more idea comes that, I mean, what is the unitary transformation doing? It's just multiplying a column vector on the left. But remember, this is a column vector times a row vector. So, so the row vector also better be multiplied from the right. Okay. And the row vector is obtained by taking conjugate transpose. So on the right also you get a conjugate transpose. So, so basically this definition sort of gets forced out here. And I mean, you may ask, okay, so here, I mean, because there are no complex numbers, I mean, though I kept saying that this is ket 1, 0, and when I take the bra, I take conjugate transpose, but this looks as good as transpose. But surely, I mean, if this was alpha comma beta, this would have been alpha star, beta star. So, I mean, one thing like a slightly deeper mathematical reason is that, okay, I mean, if all I want is a row vector, why am I insisting on taking the conjugate transpose? Why not just the transpose? So the answer to that is that, remember, I mean, there is this underlying in the inner product structure in the space, right? We always want to respect the inner product in question. So if I just take transpose, that operation is not basis independent. I mean, the definition of the transpose depends on the choice of the basis. But conjugate transpose actually does not depend on the choice of the basis. Okay, so so once you have inner product structure, then you can abstractly say that what is so here is a vector. Okay, call it ket V. What will be the bra of V? Okay, so bra of V will be, as I said, row vector is a linear map. So bra of V will be the linear map which sends an arbitrary vector, which I'm let's say I call it W.
So is the bra
Yeah.
of V, is it the adjoint of I mean, are you define it using some adjoint
No,
qualifier? Because
well, I
that
mean,
is
you don't have to go so far. Okay, so adjoint will come when you're talking of matrix or linear transformation. So this is something that you define before the adjoint. So let me fix. So here is the vector V, which I'm calling a column vector. So what is the bra of that? Okay, in tuples is a conjugate transpose, but more abstractly, what is it? It is the linear functional which maps an arbitrary input vector W. So W is this A comma B in red. So it is the linear function which maps an arbitrary input vector W into the scalar inner product of V comma W. Okay, so this map from W to inner product of V comma W, it's a linear function. Okay, and I mean it's a well-defined linear function, abstractly well-defined. So this linear function is what I'll call by bra V. Okay, and now if you want to write it in tuples, remember when I do inner product of V comma W, there's a conjugation done for V, right? So that is why this becomes a conjugate. This is the inner product, basically what I'm doing, but then this part is to be conjugated. Okay, so this is the only basis independent definition that would make sense. And the adjoint that you are saying will be the next step. Like suppose I want to do expressions like inner product of V comma MW, where M is a matrix acting on W. Can I instead re-express? So this is a scalar. Inner product of V comma MW is a scalar, and it is also linear functional. It maps an arbitrary input vector V, so arbitrary input vector W into. Let me write it down somewhere.
No, I wanted to know how the proof for the claim that conjugate transpose is basis independent, but I sort of got it. I mean,
Yeah. So I've now defined conjugate transpose basis independent using the inner product. But what you are saying is this: that V comma MW, right? So this is a linear map. W maps to V comma NW, right? So this is a linear map. And so if it's a linear map, then this should be expressible as bra of something, right? And then, I mean, you can check that. So that something will be the conjugate transpose of the matrix M, which I'm again calling M dagger. Okay. So this defines the adjoint. So if you're working abstractly, what is conjugate transpose of matrices? Okay. Conjugate transpose again is a basis dependent way of describing this. The conjugate. So again, transpose of matrices would actually have been basis dependent, but conjugate transpose of matrices is basis independent. That is because you can define it this way. So here is a matrix M. Okay, look at this expression V comma MW. This is a linear map from W to complex numbers. So it should be expressible as bra of some vector. There. Yeah. So this is because every linear functional can be associated to a vector because of the existence of the inner product. This is a little fact that you need to prove. So this has to be associated to some vector, and so the mapping from V to that vector is given by M dagger, and you can check that this mapping is also linear. Okay, so this is abstractly the definition of linear transformation M dagger. So this is called the adjoint. So this is all done in linear algebra books. I think it's you probably already seen it in your linear algebra books. Okay. If not this abstractly, but did you see this, Hari?
Yes. Okay.
Yeah. Okay. Yeah. So this is again mean, when people do normal operator spectral theorem, usually this thing is done. Okay, so let's go down. So I now know mathematically how to describe this process. Okay, and the discarding is the trace out operation, which I also described last time. Okay, so this is what general quantum operations are. And now we will look at this specific quantum operation. Okay, so okay. So examples of quantum operations. So I saw the most general ones. So quantum operations. So you've seen the most general one, but there are some specific ones which are of interest. So let's come down. So let's recall this. So the first one would be attach an ancilla. Even that's a quantum operation. Okay. So very simply, it attach an ancilla initialized to a fixed state. Okay. So earlier the fixed state was the all zero state, but more generally this is also a quantum operation. Okay. So this is the operation which sends rho I to rho I tensor sigma A. Sigma A is fixed. Then another example will be unitary transformations. Only unitary transformations. Okay. So that will map rho I to U rho I U dash. So U is a unitary matrix on I. Then the third one that you already see. So I'm just separating out the steps basically. And then I'll add a fourth one, which is important. I mean, the fourth one can be realized as a combination of these three. Okay, we'll see that, but it's important enough that we spend a lot of time talking about. So this is the what is called the trace out, discarding, marginalizing trace out. Okay. So that will send trace out system A. Okay. So what does it do? It takes a density matrix on IA, an arbitrary matrix, and traces out the A subsystem. Okay. So these are examples of quantum operations. And now, okay, so I'm just, we have all seen it in the general definition, just repeating myself. Now comes the fourth one, very important, which is called measurement. Okay. Yeah. So remember that, I mean, this is all mathematics, what you described, but actually, I mean, this mathematics actually describes real physical operations, okay? Operations on real physical systems in the laboratory. So as I said, like if you want to realize a qubit, a two-dimensional quantum system, so there's actually a real physical system, the spin of an electron. Okay, that is correctly modeled by the vector space C2. So they're actually physical objects whose mathematical description of their physics involves these matrices. Okay. Now, I mean, if you're doing an experiment in the laboratory, so okay, so let us see how you do this in the laboratory. So attach an ancilla just means, so let us say there were some electron spins whose state was described by this density matrix. And now attach an ancilla just means, no, no, school name. জলটা খেয়ে নাও, গরম করে। So attach an ancilla means I take some additional electrons, okay, which are initialized to this fixed state sigma, and I just bring it into my laboratory system. These electrons are prepared in a different machine, okay, in this state, and now they are brought into my machine. So this is physically just bringing them side by side. So that is the first operation, attach an ancilla. Unitary transformation is the complicated one. So unitary transformation actually in a real lab would mean you apply some maybe some microwave pulses or some lasers or something like that, or some electric and magnetic fields and all. So this is how you implement this unitary transformation. So the mathematical description of unitary transformation, physically there will be some microwave pulses or lasers and light. Okay. Then trace out system A is again very simple. So I have some electrons whose which will break into two bunches, I and A. Okay. So they had a joint description state, and what I do is that I will just remove these electrons, okay, from the second bunch A. Okay, so this is what it corresponds to. So similarly, the fourth one, measurement, also corresponds to a very important thing in the laboratory. The measurement actually corresponds to, as the name says, a real measurement. So you have some electrons and they are in some prepared in some quantum state, so they discover some density matrix, and I want to measure some property of that. Okay. So basically, so how is this done? Again, you apply some micro pulse or some laser, okay, and then this laser will fall on those electrons, get reflected somewhere, and then the reflected beam will be detected in a laser, in a detector, and the detector will get a voltage pulse, and then like on an oscilloscope something will spike up. So that is the measurement. Okay, so something like that will happen. So measurement corresponds to our intuitive notion of measurement or observation. And mathematically, what does this correspond? Okay, so mathematically, it corresponds to the following.
Shouldn't you be destroying the I register?
Let's define a more general one. Destroying just means you'll be discarding the I register. Okay, so let's define the most general. So yeah, so let me explain what this is. So here is my system, input system I. So this is in some density matrix, rho I. So this looks really bad, but let me walk you through. So what is this? So as I said, what I'm doing, I was doing some observation. Okay. So the outcome of the observation is a classical thing. I mean, it is some voltage spike, I say, and like, okay, so observation can be of continuous variables like position. Okay, I want the position of the electron. I want to measure the position of the electron, or I want to measure the momentum of the electron. Okay, so the outcome observations can be continuous variables, or they can be discrete variables. So now, since we are doing computer science, we prefer discrete variables out here. So discrete variable could be, let us say, my electrons are in some confined space, some box, and I want to know whether the electron is in the right half of the box or in the left half of the box. Okay, and so that I'll capture by, you can see there's this additional system, additional register C that I'm saying. The word C is to remind you that this is some classical register. So the outcome of the register is a classical quantity, outcome of the measurement. So in this case, let us say X will be a single bit. So X will take the value 0 if the electron is observed to be in the left half of the box. It will take the value 1 if the electron is observed to be in the right half of the box. Okay. Let us say I is just a single electron. So I'm talking of a 2x2 density matrix, which describes the state of a single electron spin. And I'm measuring, yeah, so if I'm talking of spin and if I'm measuring it, then I'm measuring whether the spin is aligned like along the positive z-axis or along the negative z-axis. So if you measure spins, remember, I mean, spin is described by two-dimensional space. So if you measure spin, it basically means you're measuring in the computational basis. So as I said, okay, the two-dimensional space C2, I'll think of in the computational basis ket0, ket1, and right, somewhere here I wrote ket0 is mathematically the 0th standard basis vector, 1, 0. This is the first standard basis vector, 0, 1. So what does this physically correspond to? So remember, like, I mean, for this cartoon diagram of an electron, so electron can be thought of as spinning along some axis like this, and the electron has a intrinsic magnetic moment, which is called a spin, and this can be measured also. And the magnetic moment makes it appear as if the electron is like a charged ball which is spinning around this axis in this direction. Okay, so this is the cartoon diagram, and if I have to, and I earlier said that this spin can be aligned along any axis in 3D. Okay, and but I mathematically capture it by a 2x2 complex density matrix. I don't capture it by a 3-dimensional object, but by a 2-dimensional thing, 2x2 matrix, because of important physical reasons. Then if I try to measure it, so if I try to measure it, the standard measurement that I will do is whether the spin is aligned along the positive z-axis or it is aligned along the negative z-axis. So whenever you set up a measurement apparatus for spin, you normally you cannot measure things like what is the axis
I have a
for a
very
single electron. Yeah, so let me finish. So this is one of the, I mean, really idiosyncrasies of quantum mechanics, that if I have to try and measure the direction of spin, so I have to set up some equipment for that. But the only equipment that I can set up and measure will be something that will be a 2 outcome. So this is captured by the fact that the spin is mathematically captured by 2-dimensional space. So if I have to really measure it, I can only construct 2 outcome measurements. Okay, so I can surely fix any axis in 3D and call that my z-axis, and now I can say, is the spin aligned in this direction or in the opposite direction, parallel or anti-parallel? So this is the terminology. So the outcome of the measurement is always a 2 outcome, 0 or 1. So though the spin can be aligned along any axis, so but if you set up a measurement apparatus, you have to make a choice of an axis, and all you'll get is whether it's aligned parallel or anti-parallel. Now, of course, if I have many electrons, and let us say presumably they are all independently aligned along the same spin, then surely you can measure the first one, let's say around this axis. The second one you can measure for this axis. The third one you can measure for some other axis. And then you can do some statistics and figure out, oh, like actually the true state of the electron was aligned along some axis out. So you can do these things, but then you'll need several independent copies of this system. You cannot do it one copy. With one copy, you have to make a choice of an axis. Okay, and so the choice of that axis basically is the choice of the special basis of the computation, and then the outcome of the measurement will always be a two-state classical thing, 0 or 1. Yeah, Shantan, you're saying something.
Okay, so two questions. One is a physical sort of question because I don't know much physics. So the spin thing, you said it's a magnetic something. So
Yeah.
is it like there's a bar magnet sitting there with North Pole at the top, South Pole at the bottom?
Yeah, you can think of it that way.
Acha. But you are saying that that magnet cannot turn any other way but north-south or south-north. That's all that it's
No,
allowed to
if
do.
you have to measure it. So if you don't measure it, so we know that the spin can be along any axis in 3D. Okay. So
What? Oh, it's a vector. So yeah. So that leads to my second question. So before measurement, right? So how do you describe it? Is it a pure state? just a single
no.
electron?
So yeah. So in general, it's a mixed state. So the pure state description will be spin along any axis in 3D.
Acha. So if you fix the axis, that is a pure state. Then I can write it as a ket. But if the thing is like if the magnet is dancing SA, that is the mixed state description that we know about.
Well, yeah. I mean, yeah. If you can call it dancing, or you can say that the with probability half, let us say. Let me check this. Sorry about that. Yeah. Okay. So let me repeat what I was saying last. So let's go to this picture. Okay. So to remind everyone, so so the jargon pure state means that the density matrix is a rank 1 density matrix. So remember, if it's a rank 1 density matrix, it can basically be written as the ket times the bra of the same vector. Okay. So then you can succinctly say that, oh, it's a pure state, so I will not use the density matrix formalism. I'll just say what is this vector? What is this vector ket v? And then there's bra v out here. Okay. So people often, in short, say that, oh, this is a pure state described by this vector. So, so if you're talking about the rank 1 density matrices, electron spins in rank 1 state, so these are called the pure states. So they physically correspond to spin along a particular axis, so along any direction in 3D. But more generally, of course, you can have a probability distribution, okay, of these pure states. So that will be a general density matrix. So I think I should say more about it, which I'll do shortly. So yeah, so physically a general, the most general state of the electron spin is a probability distribution of axis spins, or like pure state spins. But nevertheless, if you want to measure, you have to make a choice of your measurement axis, and you can only measure along that axis. And moreover, the amazing thing, I mean, these were like landmark experiments which were done. So fine, I have to make a choice of the measurement axis, but if you measure it, all you'll see is that either the electron spin is aligned parallel or anti-parallel. So actually, I mean, the experiment is amazing. So anyway, this is not a physics. So if I was doing a pure quantum course, I would have actually described that experiment. So that's called the Stern-Gerlach experiment. But yeah, so essentially, let us say I make a choice of I make a choice of measurement axis, which is like the z-axis. So even though the true state of the electron spin is not aligned along the z-axis, nevertheless, if I measure it, I'll see it aligned along the z-axis. So this is one of the first mysteries. And of course, when the experiment was originally done in 1930, I mean,
and this z can be any arbitrary direction,
it can be any arbitrary direction. Yeah, so that I'm calling my z. So no matter what is the true axis of the electron spin, on measuring, you'll always see it either aligned parallel or anti-parallel. And moreover, the amount of magnetic moment in the direction is fixed. So, I mean, there is an analogy to bar magnet, but even the strength of the magnet is fixed. So that's the amazing thing. So what do you mean the strength of the magnet? Let us say I measure the electron spin, okay, along this axis. I'm working along this axis out here. Okay. So as I said, I will either see it aligned parallel, so which means that the electrons which are aligned parallel will all end up at a certain distance in this direction of the detector. Let us say this is my center of the detector. Okay. All the electrons will appear at a certain distance here, and then there will be another bunch of electrons which will end up here. That's it. So the interpretation of this is that and then I mean you can use identical samples and then measure along some other axis. You'll still all see it either aligned parallel, which is electrons landing up here, or anti-parallel, which means electrons land up here. So this is the amazing dichotomy that that whatever the true direction spin may be, measurement is causing a collapse. In the sense, measurement is forcing the direction to be aligned along the axis of measurement, and the amount of magnetism is also fixed. Either it's parallel, all of them land up exactly at this distance, or all of them land up exactly at this distance. So that's it. So this is the discrete nature of electron spins. So electron spins look continuous, but once you measure, it starts looking discrete. So this is really a qubit. So to describe the full mathematics of physical behavior qubit, you need 2x2 density matrices. But if you do an observation, it just starts looking like a bit. Okay, so let's understand what this measurement corresponds. So let us have decided to measure along the z-axis. I mean, let's have chosen the up-down thing as my z-axis. That's my measurement equipment, and that fixes the computational basis. So the outcome of the measurement would be either aligned parallel or anti-parallel. Parallel, let me call it ket 0. Okay, so that will so this x is just a single bit. So if x is equal to 0, ket 0 just means that the electron spin has been measured. It has been found to be parallel in the positive z direction. Ket 1 means the electron spin has been measured and it has been found to be anti-parallel in the negative z direction. Okay. So this summation is only over two things. Okay, a 2-point sample space 0, 1. Then the outcome of the measurement has been recorded in this register C. So C is basically the register which records the outcome of the measurement, which is either 0 or 1. And going back to what I did out here, so the classical all zero state is given by ket 0 bra 0. Okay, and that's precisely what I've written out here. Okay, the classical zero state, if the outcome was 0, then this register C, this classical register C, is now set to 0. So this will be ket 0 bra 0. If the outcome is 1, this will be ket 1 bra. Okay. Now, condition on the fact that the outcome was 0. What is this state? So this has been fixed to 0, and whatever this state is is now independent of this, right? So this is like a probability distribution. I mean, if I had a joint probability distribution on I and C, but on C the probability was fixed. Okay, then whatever the probability distribution I is, I can say technically that it is independent of C. So the same thing is captured out here. C, as let us say, is now fixed to ket 0. Okay, the classical outcome is 0. So whatever this is technically independent of 0. Okay, so I can write the tensor, and now I'm saying what will be the resulting state of the electron. So what happens is described mathematically by this operation. So for outcome 0, there is this matrix lambda. It is a 2x2 matrix for me now, and similarly lambda subscript 1 is also a 2x2 matrix. And what is the property of this matrix? So lambda 0, lambda 1 are positive semi-definite matrices, and the sum of these matrices is the identity matrix. So in this case, it will be the 2x2 identity matrix. So more generally, I mean, this is my input Hilbert space I, and this and when I do a measurement, so X runs over the measurement outcomes. Okay, so the measurement outcomes are classical, stored in a classical register, and if I observe the xth measurement outcome, then the quantum state on I becomes, okay, this expression, so which can be written as square root lambda x rho square root lambda x. So what are the lambda x's? The lambda x's are the matrices that act on the system I. Okay, so they're I by I matrices. They're positive semi-definite, and summation over x lambda x is the identity operator on I. Okay. And now this is the square root of the density matrix. So what is the square root of a positive semi-definite matrix? So let us say I express the matrix in its eigenbasis. So all I do is that I keep the eigenvectors the same, but I take the square root of the eigenvalues. Okay. So this defines a new operator. Same eigenvectors, but the eigenvalues have become square. So that new operator is this square root of lambda x, and you can easily see the square root of lambda x times square root of lambda x. So this is just square the eigenvalue. So I'll get back lambda x. Okay. So in future, I'm also going to define log of lambda, things like that. Okay, the definition is the same. Go to the eigenbasis. Okay, just change the eigenvalues, keep the eigenvectors the same. Okay. So this is the full definition of the measurement operation. Questions?
So rho superscript I is the is whatever we have when we are not measuring the system.
Yes. So this is what we start off with, rho superscript I. After the measurement, I get this state, but see that it has become a joint state on Ci. Okay, so there is the classical outcome C. So that is what my measuring dial sees. Okay, and I mean, if I'm measuring position, this may look like is in the left half of the box, the right half of the box. If I was measuring spin, I've told you in some more detail what is this spin, parallel or anti-parallel, spin up or down. It's also called. Okay, so there is this classical outcome, and if the classical outcome is X, then the state of the quantum system is given by this expression: square root lambda x rho I square root lambda x.
Okay.
So, I mean, of course, we have to check that this is a, I mean, remember, whatever we are doing, this has to be, it has to be density matrix. So this was the density matrix rho I. Is this a density matrix? So let us check that in the next page.
No.
Okay. Right. So measurement. Small lambda normally used for eigenvalues. And what is the property? The set of lambda x's. Okay. So these are positive semi-definite. To the property with some x lambda x. So let us check what is the trace of the right hand side. At least let's check if the trace is 1. So trace is linear, right? So it is summation over x. Now this is a tensor product of two things. So that trace respects the tensor product, right? So trace of so this is something that you can check. Trace of M tensor N is trace M tensor trace N. You can just check from the definition of tensor product of matrices. So this is, I can write trace of square root lambda x rho square root lambda x, okay, times trace of this guy. But this I know, this is like ket 0 bra 0. So this is basically, in fact, a diagonal density matrix with a 1 in the except location and 0 everywhere else. So of course this is trace 1, no problem. So, but what is the trace of this? So here I'll use a cyclic property of trace. So I'll say that this is trace rho, but I'll now move square root lambda x to the right. So square root lambda x times square root lambda x will give me lambda x. Okay. Again, I'll use the linearity of the trace. So this is trace rho. I'll move the summation inside lambda x. Let's see. Okay. But now I know this is trace rho, and this was identity, right? So this is this clear? So this is indeed a trace 1 object. Now let us see if this is positive semi-definite. So let us see what does this look like. So what does the right hand side look like as a matrix? Okay. So actually the right hand side has a block diagonal form. So remember, I mean the right hand side is a system over the state over the register Ci, C for the classical outcome and I for the original quantum system. And so the vector space is C tensor I. And for such tensor products of vector spaces, I have the tensor basis, I have the lexicographic order. So in the lexicographic order, so what it looks like is it becomes block diagonal and the blocks are labeled by X. Okay. And the XF block is square root lambda X rho square root lambda X. Okay. So the blocks act on the system I, and the name of the block is given by the system C. So, and this, Let's pull it up here so that you can see. So, so this is, remember, so what was this? This was the density matrix which had a 1 in the exit location of C and 0 elsewhere. Okay. So that is captured out here. So it is a 1 in the exit location, 0 everywhere else. Okay. Now, what will that 1 be multiplied by? Definition of TensorFlow, that 1 here will get multiplied by whatever matrix is out here, and that matrix is square root lambda x rho square root lambda x. Okay. So this is the story of the except location. Then of course, like as x sums over, so they are just different blocks. So this is block diagonal. Okay. So this is block diagonal like this. And I've told you what the except block is. This clear? So this is the pictorial description of the matrix. Is this clear? Okay. So now, if I have a block diagonal matrix, okay, then checking whether it's positive semi-definite boils down to checking whether each of the blocks are positive semi-definite. So this is something that you can again easily check. Okay. So several ways of checking it. One way, I mean, you can actually check by multiplying on both sides by a certain vector. I mean, form the quadratic form and then see that it's always positive. Or you can ask what are the eigenvalues of this matrix. So first of all,
I mean, even if you do the quadratic form thing, ultimately it will distribute along the block. So it's the same thing. This is much better.
Yeah, but I mean, it's time we should also start getting a feel of the eigenvalues. So what are the eigenvalues of this block diagonal matrix? So just find the eigenvalues of this matrix, union the eigenvalues of the next block, so on. So the eigenvalues are just the eigenvalues of these blocks. Okay, the off-diagonal blocks are 0, so they don't cause any problem. So so it's easy to write down what are the eigenvalues of this matrix, what are the eigenvectors of this matrix. So there's just the union of the eigenvalues and eigenvectors of the corresponding blocks. So for this matrix to be positive semi-definite, each of is equivalent to saying that each of these blocks has to be positive semi-definite. So let us take the xth block and check that this is positive semi-definite. Okay. So so RHS positive semi-definite is equal to saying each block positive semi-definite. Okay. And now what is the block? Okay. So now let us look at the except block. So this is where it is probably better to use the quadratic form. So I want to check that this is positive semi-definite claim. Square root lambda x rho square root lambda x is positive semi-definite. So proof is simple. So let us say I take a vector v, okay, and I'm forming the inner product v square root lambda x square root lambda x. I'm forming the quadratic form. Okay. And now I'll use the property of the adjoint, which I said. So I have to take.
Pranam, had you assumed that lambdas are themselves positive?
Yeah, I've written them.
Okay. Okay.
Square root lambda x dagger v rho square root lambda x v. Yeah, all of them are positive semi-definite. So this is equal
but
to.
This is generally, I mean, for measurements, this may not be true, right? I mean, For a measurement, this may not be true, right? For a measurement, you can have
Well,
any sort of.
you can give a slightly more general definition of measurements, but I mean, yeah, let's
Yeah,
see.
for us, this is fine. For us, this is fine.
Yeah, I mean, you can give a slightly more general one that I'll drop the lambda x positive semi-definite, but then I have to so you can give a slightly more general definition. So I'll drop the fact that the lambda x is positive semi-definite, but I'll still keep the requirement that summation lambda x is identity. But I'll put a lambda. Okay, so now square root will not make sense. So let me put lambda prime. So I put lambda prime here, and I put the lambda prime dagger out. So that also, I mean, will be positive semi-definite. Same, it's the same kind of proof. Oh, dishwashing taking need to be. So yeah. So remember, lambda x was positive semi-definite, the way I defined it. Square root lambda x is also positive semi-definite, right? I took square roots of the eigenvalues, they're still positive. So square root lambda x is a positive semi-definite matrix. So it's also a Hermitian matrix. So the dagger goes away. This is square root lambda x v rho square root lambda x v. So now remember, rho was a positive semi-definite matrix. So if I take any vector w, so I'll just call this my vector w. So if I take any vector w and multiply it on the left and the right, I'll get a positive number. Okay. So in particular, now my w is of the form square root lambda x times v. So no problem. So this is greater than equal to 2. So that finishes the proof. So this is a positive semi-definite matrix. Each block is positive semi-definite, and the overall trace is 1. So what I've got is a density matrix. So this is a density matrix on the system Ci. Okay, and the way I'll physically interpret it as is that, okay, C is the classical outcome. It is the exact outcome of the measurement. And if it is, if I observe outcome X, this is the resulting state on I is this. Okay. The only, to make this picture complete, I have to ask what is the trace of this thing, right? So in general, the trace of this is less than 1. So only when I add up all the traces of all the blocks do I get 1. So this allows me to interpret the following. So the probability of observing the outcome X. Okay? So you may have heard that, I mean, the outcomes of quantum measurements are probabilistic, and we are doing information theory, so there are probabilities everywhere, right? So the probability of observing the outcome X is nothing but the trace of this quantity, right? So the summation of all these traces is 1, as we just checked. So I can interpret the contribution of the xth block to the trace as the probability of observing the outcome X. And by cyclicity, this is nothing but trace of rho lambda x. So this is the definition. So the definition of observing the xth outcome is this trace. Okay. So now I have a nice physical description that ties to a mathematical description. So I've done a measurement on my systems. My system was in the state rho I. I've done a measurement. The measurement is mathematically described by this set of positive semi-definite operators, lambda x, which add up to the identity matrix. So the index x I interpret as the classical outcome. So if the classical outcome is x, okay, the state, the quantum state collapses to this expression, okay, and but if I have to treat it as a quantum state, I have to renormalize it by the trace, because this has to become trace 1. I know it's positive semi-definite, so to make it trace 1, I have to renormalize. And the renormalizing factor is the probability of observing the xth outcome, which is this. Okay, so that's the full description of the physical process of observation. Okay. So this is the classical outcome. This is the probability of the outcome, and the collapse state, if I get the exit outcome is this divided by x. Okay, is it clear?
So I just have a comment. So
Hmm.
apparently, so this observation thing, I mean, till the description of the measurement, everything is fine. Then we describe the observation thing, right? Observation just says that you get, I mean, if you're a probabilist, you understand what observation means. That basically, suddenly nature decided to actually, nature decided to actually give you one of these x's and not create this whole state, which is the summation over x. But nature decided to give you one of these x's, and that x
Hmm.
appears with the probability, which is the trace of this guy. So you have to normalize and all those things. So essentially, you're conditioning on x.
Hmm.
But physically, I mean, if you think a little deeply, there's a difference. So if you apply a measurement operator, you get this whole guy. But if you measure plus observe, then you get 1x for one guy, and the thing collapses. That's called collapse. And I mean, apparently there is a rule in physics which tells you that actually the probabilities come like this, and that rule is called Born rule. And apparently that is sort of like an axiom in quantum mechanics.
Yeah. I mean,
Yeah.
so I'm not saying anything different from the axioms. So the axioms of quantum mechanics tell you that this is a valid quantum operation, and from there you can mathematically derive that this is the most general quantum operation. Okay. So from those axioms, so the Born rule will come in somewhere there.
Achha.
So the Born rule is already here. So this is the Born rule. So what you're calling the Born rule is this.
Okay. Yeah. Right.
Okay.
Exactly.
Yeah. So I mean, either you can state the axioms, and the axioms are stated in a very simplistic language, and then you can do a lot of mathematics and come up with this formalism. So that's a fair way of doing things. Okay, so books do that. Or because I mean, we're in a hurry and we're doing information theory and we like operators and mathematics, so I'm just stating it as the most general. But ultimately, I'm not doing anything beyond that.
But it's pretty weird, right? That I mean, this math is very pretty. But
the math is very pretty. Yeah.
But what is weird to me is that reality should behave like this.
True. Yeah. So I mean,
your choice of these lambdas. I mean, what lambdas are up to me, right? I can decide whatever the lambdas are, and no matter what this state is beforehand, my choice of lambda will essentially determine the outcome. So I can come up with a completely different set of lambda x primes.
Yeah. And it's a different measurement.
That's weird.
Yeah. So so I mean, the more you think about it deeply, I mean, realize that there are a lot of deep philosophical things. There's a lot of mystery in it, and I think who said that? Maybe it was Bohr only who said that anybody who has seen quantum theory and is whatever, forget exactly, and is not stunned by it or whatever, and is not confused by it, has not understood it. And I mean, if you take the axiomatic viewpoint, like these are the axioms of quantum mechanics and whatever, like these are, then you have to argue that they're physically reasonable. I mean, there's a lot of things. So these are called foundation of quantum mechanics. I mean, if you go down that line, so you can say, okay, these are the axioms I'll work with. You can also ask what happens if I drop one of the axioms and what are the mathematical consequences of that. You can also say that, okay, I mean, why are these axioms seemingly fundamental? I mean, what do they mean physically? And then like if I were to tweak one of the axioms, then it will change some physical properties, and then you say, oh, that doesn't look like that doesn't look like a good thing, okay, or that I mean, that does not look like how nature behaves, and so on. So I mean, to quote another famous quantum physicist, Asher Perez. So quantum mechanics takes place in a laboratory. It does not take place in a Hilbert space. Okay. So really, I mean, you should remember that all this has been abstracted out from decades of very important experiments done by many groups all over the world, lots and lots of experiments, and it has been abstracted out from that. So it's a tremendous intellectual achievement. Okay, so the math comes later, the experiments came before, and the way to make sense of it slowly led to this formalization, and I mean, even after the formalization was done, already by late 30s, von Neumann formalized it with Hilbert spaces. Okay, but I'm sure von Neumann and the people at that time did not realize the deep consequence of this. Only now we are realizing it. And these days, the more we do quantum information theory, okay, and that's why, I mean, physicists are also attracted to this, including like the most esoteric physicists in the world, like the string theorists are attracted to it now, because they realize that the more they study the mathematical consequences of these axioms, okay, and a fair amount of mathematical work has come to come up with this formalism, and there's still a lot of juice left to be discovered there. So the more they think about it, the more juice is coming out, and that is making them rethink about how nature behaves, or may behave, or should behave, okay, and is giving them physical insights. So these kind of mathematical consequences are giving them more physical intuition. Okay. So it's a very exciting intellectual thing going on, and now I mean these insights that have been made in information theory and computer science are now going back into physics, and the physicists say that they are realizing new things about nature, getting more intuition. Sure, yeah. So yeah, I mean, a more traditional course, I mean, which is maybe trying more towards physics and foundation quantum mechanics, would first take the axioms and derive this formalism. And there's a fair amount of lectures that you could do to derive. But anyway, we are going to assume that this is the mathematical way of describing it, because we are in a hurry. We want to see the information theoretic consequences of these operators. And in fact, our previous director, Sandeep Trivedi, so he is also fascinated by this thing these days, and I mean, and his advisor is John Preskill, I mean, who is fully into I mean the quantum information aspects of quantum physics now. So I mean, yeah, I mean he's a I mean physicist by training, and I mean most of his life he's done standard physics. I mean, but I think Sandeep Trivedi said that I think the last pure physics paper Preskill wrote was with Sandeep Trivedi long time back, when I think Sandeep Trivedi had just graduated from Preskill, was doing his postdoc, and that's the last paper they wrote together. And he says that's the last pure physics paper Preskill wrote, and after that Preskill said, okay, I mean that kind of physics is all, I mean, not interesting anymore. The real new advance in physics will come from these considerations. Okay, and Sandeep said he didn't believe Preskill at that time, and he continued doing standard physics, but now he thinks that Preskill was right, and I mean he thought much ahead. So now Sandeep Trivedi is also trying to understand these things. Okay, but anyway, I mean the work has been done for us by other brilliant people. So by the way, this formalism of operators and all is maybe 40 years after von Neumann or something. So this is the work of Krauss and our own Sudarshan and all. Okay. So these operators, I mean this three-step process basically is the work of Sudarshan and Krauss. Yeah. So any further questions? Else we will stop the lecture.
ECG Sudarshan,
yeah.
Krauss.
Yeah. So unfortunately, he didn't get as much credit as Krauss. Sudarshan has had a lot of pioneering discoveries, and he didn't get enough credit for many of them. He was also asked in an interview if he thinks if there is some systematic racism, and he said no, there's nothing systematic. But yeah, so who knows? Anyway, but yeah, I mean definitely, I mean Indian science is at its best now since maybe the time of Jagdish Bose and Satyendra Bose. Now, so I mean the future for you guys is bright. So, yeah, you'll probably, I mean I think by default you'll be respected much more, and you'll listen to much more than what was even the case 20 years back. Yeah, so let's stop here. Any questions, Hari? Any doubts? Okay, so we'll, yeah.
Yeah. So I have some doubts, but I'll ask in the next class. I have a meeting.
Okay. Now, interest on the recording.